So welcome to today's lecture. We will continue from where we left off last time. So last time we revisited the wiretap channel and we quickly saw how we obtained the inner bound, the achievability. Then we proved a matching converse, one-shot converse. So we remarked that one-shot converse does not imply a single letter IID converse, but there is a single letter IID converse which is known, and you are encouraged to see the proof from Elga Malkin's book. Now, then we started with the first multi-terminal channel, which was the multiple access channel. And we just defined the channel and the setup of the problem. Okay. So any questions, doubts, comments about material we covered in the last few lectures?
The wiretap channel converse single letterization is very much open even in classical till now.
No. Single letterization is known classically. Okay, it is exactly. I mean, wiretap channel. This is the bound that we proved for the wiretap channel, right?
Yeah.
So
I'm asking that this can
with
be
the Markov chain. I mean, under this Markov chain. Yeah. So this is known as the single letter level in classical asymptotic IID.
Okay. No, I'm saying we did a trick for the point-to-point case, right? That we proved the bound and
we obtained a single letter bound for point-to-point from the one-shot bound.
Yes.
As far as I know, this process is open.
Okay.
So the question is, can you convert the one-shot bound, which we have out here? Okay. Can you convert the one-shot bound into a single letter bound? Basically, the obvious one, that mutual information between U and Y minus the mutual information between U and E. So can you derive this from the one-shot bound, okay, for the IID case? So we want to derive it from the one-shot bound, and if possible, we want to get to see what is the second order rate. So this process is open. It's conceivable that if you do it, I mean, you will get good bounds on second rate. Okay. Note that we can already say something at the second order level for achievability. So because we have the same bound for achievability, we can just take these quantities, but apply the channel and the encoding procedure n times in IID fashion. So all these quantities will go to their Shannon counterparts. So so what do we get? We know that the falling rate is achievable. So we have we get order. So what is the second order achievability? Maybe, I mean, we can say that R greater than max over the Markov chain. So what you get from the second order cases, that so this will be n I from U to Y. So let me put the n here. So the dependence on n is this minus the mutual information between U and E this minus, so then there'll be square root n, and then we will have the information variance between u to y minus the information variance between u to e and then plus lower order terms, so something like order log. So this actually can be achieved. Yeah, so the error dependence will appear at the second order level. So this gets multiplied by the inverse of the CDF of the Gaussian, so phi inverse epsilon, okay, and then plus the order epsilon log. So and for small epsilon, phi inverse epsilon is negative. Okay, so really, I mean, there's a minus here, but don't be misled. Phi inverse epsilon is negative, so this says that we can actually achieve something slightly more than what one would naively get from the IID theory. The IID theory will tell you you can get n times the difference of two mutual information, but the one-shot theory tells you that you can get a little bit more plus square root n times this, the difference of the two information variances. From u to y minus u2, and the error dependence comes in here, and then there's also the error dependence here because it's the constant, the big O notation does depend on epsilon, but this depends only log n on the number of repetitions. Is this clear? So this is just our usual second order analysis applied to this. So there's already something non-trivial which the one-shot theory is doing, which you could not have proved with the IID theory. And it would be great if you can prove a matching second order rate that up to second order level, this is the dependence on square root of n. So that we don't know. Yeah.
Yeah. So here's a since we already know an IID converse, and we know how to go from one shot to IID, at least for the achievability, right? Then is it not? I mean, you using that roundabout route. So
we know what is the first order dependence. So there is no doubt about it because we have the IID converse. Okay.
Right.
So the thing is, we don't know what is the second order dependence. Is it, first of all, is it square root of n? Okay, if it is square root of n, is it the difference of those two quantities? What is the dependence on the error? So this is what we don't know.
Okay.
Okay. So I mean, all that the IID converse tells us is that the second order difference is little O of n, but it could be, I mean, something like let us say n upon log n. Okay. I mean, almost as bad as n. We don't know.
Mm-hmm.
Yeah. So that's the issue. I mean, one would expect it to be square root of n times something, but is that something really the difference of those two variance quantities? So these are the open issues.
So is it not known even in the case of information spectrum setting?
Information spectrum again doesn't look at the second order rates. Okay, so it is the information spectrum is asymptotic, non-IID.
Non-IID. Okay.
This is finite block length. I think what Pranav is saying is finite block.
No, but but let me answer
from one shot
question. Yeah, from one shot you can get information spectrum mount. So the information spectrum mount, so since you asked, will be the obvious one. So the information spectrum mount will be, yeah. So let me just call it asymptotic non-IID. Okay,
Yeah.
non-IID. So this are, okay, so there, I mean, we know it is I lower bar of U to Y, maximizing over the market, the same business.
Yeah.
Minus I upper bar.
Upper bar, U2.
Yeah, exactly what you would expect from the
Yeah.
one shot. Okay, and there we have a matching converse, but that's not surprising. I mean, we are matching converse at the one shot level, which which I mean almost automatically implies the same converse for that. Okay. Yeah, because of some slight technical issue here, it does not automatically imply, but what you can do is you can take the converse proof, which I did last time for the one shot, and redo the same proof for the asymptotic non-I, and you'll get I lower bar UY minus I upper bar. Okay.
Okay.
Yeah, so really the issue is, can we go down to the IID case and get a single letter? The asymptotic non-IID is not a single letter bound, right? I mean, it is just a one-shot quantity divided by, and you take the limit and then goes to.
Yeah.
Any further questions? Hari? Did you get a chance to read about the multiple access channel and also the wiretap channel from Elga Markey?
I started reading it, but not much.
Which one? The multiple access or wiretap?
Multiple access channels.
Okay, good. Yeah. Yeah, wiretap is more or less done. Multiple access will start. Okay. So you're probably not familiar with this asymptotic non-IID business. Okay. Have you seen it somewhere? The information spectrum viewpoint? No. Yeah, it's basically the one shot. What you do is you take the one shot quantities. So the channel, I mean, there is a level n. Level n just means that your input alphabet is now x to the power n, output alphabet is y to the power n, but you have an arbitrary channel at the nth level. The channel at the nth level is not the tensor product of the n channels. Okay. So basically, a channel is described as a sequence of operators indexed by n. N is the level number. And then you evaluate the one shot, essentially, from our point of view, we evaluate the one shot quantity for the nth channel, divide the rate by n, and take the limit as n goes to infinity. So that's called asymptotic non-IID or the information spectrum. So, I mean, if you do it, I mean, we get the natural one-shot analog. So the I epsilon means in the asymptotic non-IID world is called I lower bar, and I epsilon max in the asymptotic non-IID world is called I upper bar. So that's what we do. Okay. Yeah. So let's start off with the multiple access channel. So the multiple access channel we had defined last time, but I will just repeat very quickly for your benefit. So it is a channel with two inputs and one output. Okay? So the two inputs are traditionally called Alice and Bob. The output let's call Charlie, C. And Alice and Bob are independent agents. So Alice has a message M that she gets from the outside, which she has to send. Bob gets the message M from the outside, which he has to encode and send to the channel. M and N are independent messages in the sense that they're not coming from a joint distribution, nothing like that. So M, N are independent messages, and Alice and Bob will behave independently. So Alice uses a private coin algorithm. You can see the schematic, and she encodes them into a probability distribution over the input alphabet. So there are two input alphabets, X and Y here. So this is a probability distribution over the input alphabet X. Similarly, Bob independently runs his private coin decoding, encoding algorithm, encodes the message N into a probability distribution over the corresponding input alphabet, P of Y given N. The channel does its work. So for the input symbol pair X, Y, it outputs the probability distribution on the output symbols Z. Then here is a decoder, which is a private coin algorithm. So for every output symbol Z, it produces a probability distribution over the guessed message pair M hat, N hat. And we require that the probability that the guessed message pair M hat, N hat not equal to Mn. So this means that either of the coordinates are not equal, this should be less than epsilon. And here I'm reminding you that this probability distribution is taken over the uniform distribution on the message pair n comma n. Okay, so it's the average error probability. And then I'm also randomizing over the encoding process. So there are two independent encoders. So this is randomization over the private coins of the encoding process, randomization over the channel characteristics, randomization over the private coin decoding process. So this probability over all this randomization should be less than epsilon. And we remark that average decoding error definition is essential in this problem to get reasonable rates, because the expurgation step does not work unlike the point-to-point. And basically, we discussed why it doesn't work at this stage. Okay, so now let us come up with a nice inner bound. So now the achievable results are called inner bounds for this. So let me remind you. So this problem was studied very early on. It's really, I mean, consider the simplest multi-terminal channel. So we know that there is a rate region of this form. So this is like M. This is N. So we are talking of two different rates, or maybe let's call the two rates as R2. And you may have seen in Elgamal-Kim or other textbooks that this is an achievable region, and in the classical asymptotic IID case, there is also a matching single level converse. So what does this mean? That so let us say I say fix probability distribution for the input alphabets px, okay, and py. So now the action of the channel defines a joint probability distribution, which I'll now call px, py, p of z given x. So fixed probability distribution over input. So now I have a probability distribution over the set x times y times z. Okay. So this is the underlying probability distribution on which I'm going to evaluate my mutual information rates. So the best asymptotic IID achievable result, which we'll call it inner bound. So the nomenclature inner bound is because this being a multi-terminal case, there are several rates in question. So there's a rate that Alice can get up to Charlie for successful encoding and decoding. There's a rate from Bob to Charlie, and you can now imagine that there might be a trade-off. Okay, so right, so there might be a trade-off between as you can imagine, there might be a trade-off. Like if Alice wants to send a lot of information from her hand to Charlie, it is conceivable that Bob has to pay a price. Bob can send less information, and vice versa. Okay, so you cannot just say there is one achievable rate. There is a two-dimensional rate region, okay, of achievable rates. So the rate region becomes two-dimensional, and there can be trade-offs between the two rates. So the achievable results are called the inner bound, basically what you can achieve, and then the converse results are called outer bound. So conceivably, let us say there might be, okay, I mean, maybe the true achievable region kind of looks like this, okay, and but our scheme can only achieve an inner bound like this, and maybe the best converse that one can prove is not the true achievable rate, but some region which is slightly larger, which we'll call the outer bound. So this is standard terminology, inner bounds and outer bounds. So what you so this terminology we use for multi-terminal channels. Okay, so now back to what is known about the multiplex system. So we know that any rate pair satisfying these constraints is achievable. So I'll just write the asymptotic IID version for ease of understanding. So remember, this is the underlying probability distribution. Under this probability distribution, I can evaluate this Shannon mutual function quantity, then R2 less than. Okay. So what is achievable is okay. So this is an achievable rate region. Let us understand what this means. Okay. So let us look at the third bound out here. So this is what is called sum rate bound. It's a bound on R1 plus R. Okay, so first of all, I mean, before we understand what this bound means, so any such thing, if you plot the points in the R1, R2 plane which satisfy this bound, it will form a pentagon like this, right? So this vertical line is the bound on R1, this vertical line is the bound on R2, and this 45-degree diagonal line is the bound on R1 plus R. So let's come down. Yeah. So first, let us understand what the bound on the sum rate is saying. So this should be very reasonable, okay, intuitively very reasonable to you, because let us say Alice and Bob get together. I mean, they're supposed to act independently, but let us say they get together and decide to do a joint encoding of their message pair. Okay. So then what is the best rate that they can achieve? It will be this thing. It will be the mutual information of XY. So now it is like the point-to-point case where the input random variable is now XY, okay, and the output random variable is Z, and they can achieve this rate, okay, under this underlying distribution on the control state. So this line is basically R1 plus R2 equal to even if they get together and do a joint encoding, it's clear that they cannot beat this. Okay. But now, if this was the only constraint, then I mean, what the rate region would have looked like? It would have looked like, I just extend this line. Okay. So then I should have got some kind of triangular rate. Okay. So, and in fact, I mean, that the triangular rate region would have been the correct rate region if Alice and Bob were allowed to get together and do joint encoding. But they're not allowed to get together. So what I get is a subset of this triangular region, and that is the pentagon region. So let us see. What this means. Now, let us try to figure out what is the maximum dream rate that Alice can get to Bob. And as I remarked before, if Alice is trying to maximize her rate to Charlie, then Bob will have to make some sacrifices. So Bob will have to make do with a lesser rate. Okay. So let us try to see what is the maximum Alice can get. Okay. So what is the dream rate for Alice at the expense of Bob? Okay. So now it's intuitively clear that what is the best that Alice can hope to sell to Charlie? Let us say Charlie has already decoded Bob. So that is basically captured by Charlie. Not only has the output of the channel set, but he also has the Bob's input, the code word corresponding to Bob's input, which is 1. Suppose this has happened by magic. Maybe there's a parallel side channel by which Bob's input was sent noiselessly to Charlie. Then, what is the maximum rate that Alice can push through to Charlie? That will be this mutual information. Mutual information from X to Z1. And similarly, if we want to really optimize from Bob to Charlie at the expense of Alice, so it will be the similar consideration. So it will be as if Charlie already has Alice's input for free. Okay, so he has the channel output Z, Alice's input code word X, and now the maximum rate will be the mutual information from Y to Z. So these are the bounds on the individual rates, and then there's a sum bound. So it's reasonable to believe that this will be an outer bound for the achievable rates. No scheme that you are doing should be able to do better than this. And the answer that we get for the MAC, at least in the asymptotic ID cases, in fact, this is the region. So if there is a scheme which achieves a certain rate per R1, R2, then you can cook up input probability distributions Px and Py such that the pair R1, R2 satisfy these constraints for that P. Okay, so that is the outer bound, and the inner bound that cook up probability distributions Px, Py on the input random variables. Consider this joint distribution now. Now evaluate the pentagonal region corresponding to these constraints, then any rate point in that pentagonal region is achievable. So this is known, and Elgamal-Kim proves it very nicely. Okay. So today we are going to prove one-shot analog. So before I go ahead, any questions? Is it clear what this rate region stands for? Why it is reasonable to believe that this is the optimal rate region, and where the various constraints are coming from? The constraint on R1, constraint on the individual rate R2, and the constraint on the sum rate. Okay. Any doubts? No? Okay, then good. So now I'm going to prove the one-shot analog. So you can believe what the one-shot analog will look like. So let me again draw a little bigger. This pentagonal region. Okay. So R1, R2, something like this. Okay. And let us see what we expect. So, Hari, your guess. What do you expect to be the bound on the sum rate? So the same setup. There is this fixed input probability distributions Px, Py, and then the channel gives this joint distribution on X, Y, Z. Okay, so that's the random underlying probability distribution X, Y, Z that will be working. So what is your guess, Hari, about the upper bound on the sum rate? Okay, one shot guess.
I mean epsilon like X and ZY.
Correct. The same thing which you have seen for the point-to-point channel. Same logic. Okay, and then there are this plus order log 1 by epsilon terms, and I'm ignoring that. Okay, so of course they are there. Yeah. So this is what I get, and now you can also guess if the above reasoning for the I mean, the above reasoning I had done for the IID, but there was nothing inherently IID about it. So presumably the same reasoning you can do. I mean, find out the dream rate for Alice Bob. So what would be the guesses for that? I don't know. Analogous. Yep. Go ahead. Go ahead.
Yeah. So it's like it's this thing like it's between X and ZY and the same
Yes.
thing. Like,
The same thing. Same thing.
Yeah.
So, so I mean again, sin X and Y. So you've seen this bounded algorithm, right? When you started the math,
Yeah.
not the proof.
Yeah.
So we want to prove. So yeah, so, I mean, I'm not going to write the same thing out here. This, I mean, you can label the figure accordingly. Okay. Okay. So what is the strategy? Let me start. So we'll do the same strategy as before. So remember we have the underlying distribution Px, Py, Pz given xy. And now, so we'll form the random codebook construction. So choose code words from x1, x2. So actually, I think the notation that I normally use. So x1 is the notation. x1, x2. X2 to the R1, IID from PX, okay, and correspondingly Y1, Y2. This is basically I'm repeating the class, the IID proof, but with one-shot language and time. But I want to point out an important consideration. So I mean, sort of brushed under the carpet when you do IID, but you have to pay a little more attention when you are doing the one-shot. So there are 2 to the R2 such code words, IID from P1. Okay. So choose these code words, and this forms a random code. And now the encoding strategy is very clear. So like to send message number n, what Alice does, Alice feeds the mth code word xn into channel. And to send message number n, Bob feeds yn into channel. So far, so good. Now let us look at what is the decoding strategy of Charlie. That's the same thing as before. So it is the sequential decoding strategy. But let us see what it means out here. So this is the sequential. So the algorithm for the decoding is like run through all the candidate message pairs m hat. So run through them in some lexicographic order. So they'll run from 1,1 to 2 to the R1, 2.
To do the R1 cross to do the R2. All of them. R1 cross R. Oh.
No. Yeah. Yes, clear, right? What this notation is. Okay. So in some order, so I'm writing. Order doesn't matter. You just choose the order and fix it. Let's lexicographic. So run through all candidate message pairs. So this is, and let us say Charlie is at iteration number m hat comma n, whatever the current value is. Okay. So I mean, he has presumably rejected the previous candidates, and now he's at the current candidate. And of course, the channel has outputted a symbol Z. So output Z. So Charlie has seen the output symbol Z that the channel produced, and he's trying to make a good guess about what message pair could have produced this Z. So that guess will be his m hat comma n. So now suppose we are at the particular candidate m hat comma n hat. What Charlie will do is Charlie will
What's the coin? We never specified the year. The
which one? Charlie's coin. Yeah. I mean, I'm going to tell that. Yeah. So we are going to look at this quantity, right? So this is so we are going to look at the joint distribution P X Y Z. Okay, remember this joint distribution is Px Py. What I've been saying so long. Pz given xy. Okay. So that I'm calling Pxyz, and we are going to look. Yeah. So okay. So let me. Okay, that will come in the analysis. So let me. Not get ahead of myself. Yeah. So let us look at the following. Okay. Let us look at this quantity I epsilon min. Start off with. Let us say we are still trying to borrow as heavily techniques from the point-to-point basis. So what was this? This was recall. This was just another word for d epsilon min of P X Y Z. So let me not write. Let me just write. Remind you again what P X Y Z is with the abuse of notation. So this is Px Py P Z given xy with respect to. Okay, so with respect to it should be the product of the marginals, marginal on z times marginal on xy. But marginal xy I know is also a product distribution, so it boils down to py px times py times pz, product of three marginals. So that is my I epsilon. It is the d epsilon b between these two probability distributions. So now let us say there is a function. So remember to obtain d epsilon min, so we optimize over tests. Okay? Right? Private coin tests, hypothesis tests. So this is the hypothesis testing divergence. Yep. So look at the let f3 x y z. Okay? So what is the hypothesis for every symbol triple x y z? the hypothesis test prescribes a number between 0 and 1. And the interpretation is that if we see this particular symbol triplet XYZ, we accept it with probability F3 of XYZ. Okay. Be the optimal hypothesis test. Right? So let this be the optimal hypothesis test. Now, if you look at the rate region, there were of course two other like I epsilon min terms out here. Like this is the third one. There were two other I epsilon min terms. So they will also have their optimizing hypothesis tests. Okay. So let me write, let F1 XYZ, F2 XYZ be optimal hypothesis tests, okay, for the other two quantities. So I epsilon min let F1 and F2 be optimal hypothesis tests for these two mutual information quantities. Okay. So in general, these are three different hypotheses because these are three different mutual information quantities. So clear so far? What are the definitions of F1, F2, F3? So now we will we'll have to define the strategy of decoding for Charlie. Now define. So we'll define a new hypothesis test that I'm going to call fxyz, which like in suggestive notation, I can call it intersection of these three hypothesis tests. But what it really means is it is the minimum of the three quantities F1, XYZ, F2, XYZ, F3, XY. Okay. So is the definition clear of F? So this is what I would like to call the minimum or the intersection hypothesis test. Hari? The definitions are clear so far?
Yeah.
Yeah. So the reason I'm calling it intersection is the following. So many times the hypothesis tests are 0-1 tests. Okay. So that means for some triple XYZ, the test will say, okay, accept this triple. If it's some X prime, Y prime, Z prime, the test will say reject this triple. Chalo karo. Chalo karo. So if you're looking at this 0-1 hypothesis test, this minimization is just saying that take the intersection of the three sets. So the 0-1 hypothesis tests are just subsets of triples. The test prescribes which subset is to be accepted, and you have to reject the complement. Okay. So under that viewpoint, the minimization prescription means take the intersection of the three subsets corresponding to three hypotheses. But for our I epsilon min, we don't have subsets, but rather the fuzzy version of subsets, like it's really like a fuzzy set, like you accept XYZ with probability prescribed with a prescribed probability, let's say F3 of XY. Okay. So in that case, this would be in fuzzy set theory. This would indeed be the intersection of three fuzzy sets. So it's just the minimum of the three acceptance probabilities for XY. So this is also a hypothesis test, right? I mean, it's a quantity between 0 and 1. So Charlie is going to work with this with this intersection hypothesis test. So what is Charlie's strategy going to be? Here. Okay. So run through all the candidates, and let us say if we are at the we're at a particular candidate n hat, so accept it. So with probability, accept the current candidate n hat with probability f. F is the intersection of the corresponding code words x n hat, y n hat, and the z that has been received at the channel out. Okay, so this is the strategy. It is very much like the decoding strategy for the point-to-point case, except that we have to. So there the strategy was we just take the optimizing hypothesis test for the mutual information quantity. There we had only one mutual information quantity. We just take the optimizing hypothesis test and accept the candidate message with the probability prescribed by the hypothesis. So we're going to do the same thing here, except that now the candidate message is a pair m hat. Okay. The main difference is for the hypothesis test, we'll take it to the intersection of the three hypothesis tests. So decoding strategy of Charlie is now clear. Okay. So now let us analyze the error probability and this decoding strategy. So we are going to analyze that. So this is expected average decoding error. So the expectation over the choice of the code book C of like, let us say decoding error average MN, okay, over the uniform distribution on MN. So by symmetry, I mean we only need to concentrate on, let us say, m comma n equal to, let us say, the last message in the this is sequential decoding strategy. So there is the symmetry is not there, but anyway, I mean you can easily see that the last message pair, okay, m hat n hat equal to 2 to the r1 comma 2 to the r2, the very last thing that we consider. So this should have the worst error analysis, because Charlie will only reach there after he has run through all the other candidates. So I can say that this is less than expected decoding error over the choice of the code book. The code book and the channel, of course. So, channel characteristics also.
Pranav?
Yes, Aditya.
Yeah, just to clarify, so is this the decoding, is this a way of looking at decoding algorithm correct? That for every pair m comma n, Charlie will toss a coin, which turns up heads with probability f and tails with probability 1 minus f.
Correct.
So whenever he gets a head, he'll choose that particular pair.
Yes, yes. So that is absolutely correct. So that is what the statement means. And you're like, I mean, you are given a detailed operational description of this statement, that except m hat comma n hat with this probability means at this level, Charlie will toss a coin whose probability of heads is exactly this quantity.
Okay.
Okay. And this is something that he knows. I mean, the Charlie knows the full description of head. Okay. This Z is the symbol of the channel output. He can see, and we are at the level m hat comma n hat, so he knows exactly what is x m hat and y hat. Right. The code book is revealed.
Yes.
So decoding error for R1. Okay. So now to reach this level, okay. So to come all the way to this level, 2 to the R1 comma to the R2, what did Charlie have to do? Charlie should have rejected, okay, all the previous candidates. And we want the decoding error. Okay. So when will there be decoding error for the message pair 2 to the R1, 2 to the R2? This there will be decoding error if Charlie accepted at an earlier candidate. Okay. Plus, Charlie has reached the candidate, the last candidate, but Charlie has rejected that. So this is so these are the two sources of errors. So I mean the same as before. So this is okay, so I mean this is what is something called type 1 and type 2 error. Type 1 error is Charlie rejects the correct candidate 2 to the R1, 2 to the R2. So that occurs with probability. Okay, 1 minus f x 2 to the R1 y 2 to the R2 and the given z of the channel output. Okay. So this is the type 1 error. And remember, I mean, there is this expectation, of course, over the choice of the code book. So this thing is what is called type 1 error. Okay. And more interesting, usually the type 2 error. So type 2 error is Charlie mistakenly accepted one of the earlier candidates. Okay. So let us analyze that. So what are the earlier candidates? So there can be some
M comma n prime, n prime, m prime comma n, and so
yes. So I'm saying that. So one candidate is Charlie accepted a message pair m comma n where m is different from 2 to the R1 and n is different from 2 to the R. Okay, so there are how many of them? 2 to the R1 minus 1, 2 to the R2 minus 1, and let us say something like I'll just take one such. Okay, so I'll just write f. Okay, so I accepted that by mistake. So this will be xn, yn. So these are the guys where m is not equal to 2 to the R1, n is not equal to 2 to the R2. Then there are the second guys, okay, where m is equal to 2 to the R1, but n is not equal to 2 to the R2. Okay, so this will be towards the end, I mean, for our particular case. So the second case would be m is equal to 2 to the R1, but n is not equal to 2 to the R2. So first let me write. So how many of them there are? There are 2 to the R2 minus 1 and f of x 2 to the R1, right? So then y n z, and this is n equal to 2 to the R1, n not equal to 2 to the R2. And now you can see there is the third case also. So this is the case where n is not equal to 2 to the R1, but n is equal to 2 to the R2. So these are also good candidates. So here the number of such wrong candidates are 2 to the R1 minus 1. And now similar thing, f xn y 2 to the R2 z.
this all is inside the expectation, right?
This all is inside the expectation. Okay. So these three terms together give me the type 2 error. So is this clear to everybody? Hari, is this clear to you?
Yeah.
Have you read this part of the analysis from Elgamalkin?
No.
Not okay. So I mean the same kind of analysis is done, and now you can see where the three constraints are coming from, really speaking. Okay. So let's okay. Let us try to analyze this. Okay. This is best. I just do it on the side so that you can keep looking at the expressions. So now I'm doing expectation. Okay. So let us see what is the type 1 error. So in the type 1 error, really, I mean, we are looking at the correct message candidate, 2 to the R1, comma 2 to the R2. Okay. The channel has produced output Z, but somehow Charlie did not accept it. So this is, so what is the joint distribution? Okay, so as I'm randomizing over the code book, what is the joint distribution that we get to consider? So maybe I should cramp things up. Okay, so let us analyze this. So, type 1 error. Okay, so this is the expectation over the code book and channel of 1 minus f. Yeah, so Hari, once you understand this, you don't have to read those parts from Ega molecule. The substitutes that already. So we are going to analyze this. But we know how to analyze this from what we've already seen in the packing lemma and the point-to-point channel. So here the joint distribution between this code word for X, for code word for 2 to the R1, code word for 2 to the R2, and the channel output, the joint distribution is the joint random variable, right? Px times py times p of z given xy. And we are asking what is the probability that the hypothesis test does not accept the true joint distribution. Okay. So we know what is the answer for the true hypothesis test F3. Okay. But note that Charlie is not using F3, but Charlie is using the minimum of F1, F2, F3. So things are a little more complicated here. We're a little more careful. Okay. So what is this? This is the probability, okay, under the joint distribution Px, Py, Pz given xy, okay, of 1 minus f. Charlie is of course going to use f. Okay. So I know that if this was f3 instead of f, I know this is less than epsilon, just by the definition of the optimizing hypothesis test. It was d epsilon, right? D epsilon min. Okay. But now it's f, and you can see that the error will be higher because for every point, for every triple x, y, z, the value that f prescribes is less than the value that f1 or f2 or f3 would prescribe for that. Okay, so definitely less than f3. So when you do 1 minus, so this answer will be more than epsilon. But don't be afraid; it will not be too much more than epsilon, as we'll see. So you can say that this is less than probability. So the same, just run another bracket. 1 minus f1 x, y, z. Let me write it out and then I'll explain how I could write it. 1 minus f2. Okay. Plus probability 1 x3 x1. So the reason I can write it is that so 1 minus f point-wise is less than 1 minus f1 plus 1 minus f2 plus 1 minus. Another way, another way to see it, at least if you're doing intersection of sets, is that so the good set is the intersection of these three sets for the three hypotheses. So the bad set is the union, and this is just the union bound. But more formally, I mean, this is the union bound or fuzzy sets, if you like to think of that. I'm just using that. At every point x comma y comma z, I have this inequality that 1 minus f is less than 1 minus f1 plus 1 minus f2 plus 1. So this is what I get. Is this clear to everybody? Hari?
Yeah.
Yeah. So now what do I have? So I know for f3, this thing is less than epsilon. Okay, but the point is even for f1, it is less than epsilon. Okay. So now I think maybe I should. So the probability distribution was px, py, pz given xy. And this is the same px, py, pz given xy. That's the underlying probability distribution where I'm evaluating these things. But note that for the first quantity, for f1, okay. Yeah. So yeah, so what was f1? F1 was the optimizing test for like recollect. So f1 was the optimizing test for px. Okay. I mean py, pzy, pz given xy versus. So this was the positive hypothesis, and the negative hypothesis was px times pzy. Then similarly, f2 was the hypothesis between the same positive thing. You see, the positive hypothesis for f1, f2, f3 are the same. It is the joint distribution given by px, py, pz given x. It's just the negative hypothesis which is changing. The negative hypothesis was py times p zx. And f3, same positive hypothesis. Versus the negative hypothesis was px, py, pz. Right? So these were the three hypotheses. Yes, so just please flash you what you wrote earlier. So these are the three hypotheses, right? So the positive hypothesis is always the joint distribution between x, z, and y according to this distribution. It's just the negative hypothesis which keeps changing. So what does this mean? This means that under this probability distribution, px, py times pzy, all of, I mean, f1 as well as f2 as well as f3 except the positive hypothesis with probability 1 minus epsilon. So they will reject the positive hypothesis with probability at most epsilon. So basically, I mean, each one of these quantities is less than epsilon, so the sum is less than 3 epsilon. Is this clear to everybody? Yep. Okay, good. Hari, is this clear to you?
Yeah.
Yeah. Okay, good. Very good. Yeah. So so the type 1 error is no longer epsilon. That would happen for the point-to-point case, but it's 3 epsilon. It's not so bad. Let us look at what the type 2 errors. Okay, so remember in the type 2 errors, there were actually 3 contributions to the type 2 error. So let me flash it again. There was the contribution, let us start from here, where m was equal to 2 to the r1, but n was not equal to 2 to the r2. So let us try that. Okay. Or maybe let's look at the easiest. So there is m not equal to 2 to the r1 and n not equal to 2 to the r2. So now for the type 2 errors, let us try. So we are going to look at expectation over codebook, channel, So this is the case where write n not equal to 2 to the r1, n not equal to 2 to the r. So yeah, so there was of course this thing of 2 to the r1. One, I mean the number of such candidates m hat comma n. So this times. Okay. Now let us see what is the error for this. Okay. So now what is the probability distribution that we have to encounter out here? Okay. So okay. So remember Charlie is at stage m comma n. Okay. So m comma n is the fraudulent message pair, not the true message pair, but Charlie mistakenly accepts the fraudulent message pair m comma n. So how can this happen? So the Charlie will accept the fraudulent message pair m comma n with this probability xn. Okay. So write the probability first. Space. So this is the probability. So I'll tell you what is the underlying probability distribution. So f of xn, y n, and then the channel output z that we have handled. Okay. And now, yeah. So this was the. Okay. So I have this expectation over the codebook channel. Sorry. So I mean, this probability is captured in the it's captured in the expectation. But yeah, I will write one more step slowly. Let's at least do one piece slowly. So this is 2 to the r1 minus 1. So we are going to evaluate what this what the expectation of this quantity is over the random choice of the code book. So when you do the random choice of the code book, the probability distribution on Z is independent of the probability distribution on XM and Y, right? So because all the code words for X, X1, X2, X3, these were chosen IID from PX, the Ys were chosen IID from PY. This Z is of course correlated to the code word for 2 to the R1, comma 2 to the R2, right? I mean, this is what the channel produced as output. So the actual message that was sent was 2 to the R1, comma 2 to the R2, but Charlie is at stage m comma n, so he's looking at the candidate n comma n, which is not the correct message pair at all in neither coordinates. So this expectation evaluates to this probability. So the so f of x, y, z, but what is the probability distribution? X comes from px, right? Then the code word y comes from py, and they are in product region. Z is coming from the channel input for 2 to the R1, 2 to the R2, which have nothing to do with xm and yn. So this is coming from the margin. Is this clear to everybody? This is like the point-to-point noisy channel case. Okay? This Z is correlated, is not correlated to this X and Y. Okay. So now we know what would happen to this quantity if I had F3. So this is the negative hypothesis for F3. Okay. I mean, this probability distribution is the negative hypothesis for F3. So F3 can only accept it with.
I have a very slight question. So actually, this is in the condition space for 2 to the R1, 2 to the R2. So I mean, they are not correlated, they're very much product, but it is still PZ given 2 to the R1, 2 to the R2. It is only when you take the average overall messages that this becomes the actual marginal. So yeah, I mean, it's a very pedantic thing.
I'm analyzing it for the last one. So I mean,
no, but
confused.
Exactly. I mean, you are in the condition space where you're analyzing it for the last one, but this expression, the distribution is completely product. So actually it is px, py, pz given 2 to the R1, 2 to the R2.
Yeah. But
pz when you sort of like take the average over all.
No, it is PZ given 2 to the R2, but the XY here, the XY here, this is Xn, this is Yn.
Yes.
Okay, that's why we have this. This X is Xn, this Y is Yn. And this Z is Z 2 to the R1, comma 2 to the R, if you want. So that's why they are independent of each other.
No, they are independent. That I agree. That I absolutely agree.
Yeah, with this
I'm-
distribution. So, I mean,
with this distribution, but I'm
Yeah,
just
yeah.
saying that PZ
So-
is slightly. Oh, you have already got the expect.
yeah,
I'm
yeah.
saying that you'll have
I've
the
removed the
PZ
expectation.
here. You'll have the PZ here. I mean, this will be a product. Sure, this will be a product. Absolutely. And the PX and PY will be completely independent of the PZ. Absolutely agreed.
Hmm.
I'm just saying that this is the distribution on PZ for this expression is actually conditioned on 2 to the R1, 2 to the R2 being sent. Okay. It is only
Yes,
when you,
yes. So, I mean, right from the beginning, I was analyzing decoding error for 2 to the R1, comma 2 to the R2 being sent.
yes, it is. Oh, okay.
Yeah.
Okay.
So, I mean, I think what I've written is correct. Yeah. So, I mean, actually, you have to analyze it for everything, but you get the worst numbers for this analysis. Okay, so it's sort of believable, but I mean, you can check it for yourself very carefully if you want. Okay, but given that 2 to the R1, comma 2 to the R2 is the actual message pair that was sent, I think this analysis is correct. Exactly as written. I'm not fudging it. Any more comments? Yeah. Okay. So if this was F3, then
Yeah, Pranab, no, I think what Sayantan meant was that if what is the marginal distribution of Z? So let's just see, Z is a random variable. Okay, so
Yeah,
if there is no conditioning on X and Y, then probability Z given X and Y, let's say X and Y were any junk thing which were not in the alphabet space, then either it would be undefined or it would be 0.
yeah. I mean, what is being said is the
no,
following. What is being said is the following.
nothing like
No, what is being said is
nothing like that.
following, that the marginal of Z in this
Yeah.
case,
Yes.
for
yes.
the wrong decoding, actually PZ conditioned on X
Yes.
2 to the R1, comma Y 2 to the R2.
Yeah.
That is the correct marginal.
Yes. Now
not
the
PZ.
point is that if I
Not
remove
PZ.
2 to the R1 and 2 to the R2, if I just ask what is the distribution of Z?
No, so but there is a randomization over 2 to the X 2 to the R1 and Y 2 to the R2. Remember, this is an
Yes,
expectation
and
over
that,
the
That's what Sayantan was saying.
that's what you're saying. Yeah. So that's why it becomes bona fide.
It's just Z. Yeah.
Yeah.
Okay.
So
you're
really, I mean,
including
you
the
split this
randomization
expectation into two expectation: expectation over M, comma N, and expectation over 2 to the R1, 2 to the R. So this is exactly what you do in the. Yeah.
Then it's completely.
Yeah. I mean, yeah.
Yeah, I think that is what Sayantan was saying. Like you just this two-step process. Yeah.
Yeah. Is it clear to everybody? I mean, this is exactly the same thing that you do in the noisy channel. I mean, point-to-point channel case. So the expectation splits up into expectations over just two quantities instead of a whole bunch of like code words. So it just splits up into the expectation of two coders, and those two expectations are independent. Okay. So one is the code word corresponding to the actual message that was sent, and the other is the code word corresponding to the fraudulent candidate. Okay, so this the same probability distribution. Remember, F was chosen to be the minimum of F1, F2, F3, pointwise minimum. So whatever it is less than F3. Okay, the same thing. Ex, Ey, Ez. Okay. And for F3, we know what it is. This is the negative hypothesis for which F3 was precisely defined. So okay. So this is 2 to the minus I epsilon min of X, Y, colon Z. In fact, I think I can put it here. Is this clear to everybody? Yeah. Hari, is it clear to you?
Yeah.
So this is the first step. So that I'll now analyze, let us see the rate for R1, and then you can immediately see like what is the upper bound we get for R. Okay. So now we are looking at a case where M equal to 2 to the R1, but N not equal to 2 to the R. So now this expectation one code book and channel not trigger. So this 2 to the R1 comma 2 to the R2 was sent, but Charlie mistakenly thinks that M comma N has been sent. So this will happen. Okay, so expectation of the choice of the code book, like announce the channel. Okay, but I'll not write the channel here. So Charlie gets fooled with okay, I mean Charlie accepts M comma N with this probability, so that will be X 2 to the R1, Y N, and the channel of Z. Okay. But now Z is correlated to 2 to the R1 comma 2 to the R. So what does this break down to? So again, I mean, we'll split the expectation to the expectation over the actual message pair and the fraudulent candidate. Okay. So we'll see what the probability distribution is. So I'm going to write F X Y Z as before. But what is the probability distribution? So this Z, the channel output Z, cannot be correlated to YN, right? I mean, the channel output Z is correlated to 2 to the R1 for Alice, message number 2 to the R1 for Alice, and message number 2 to the R2 for Bob. It is not correlated to the nth message for Bob. So I get PY. So the probability distribution for YN, okay, for this symbol Y, the probability this symbol Y is coming from the probability distribution PY, which is independent of everything else. And what is everything else? So there is this X2 to the R1 and Z. Now, of course, Z is correlated to X2 to the R1. Actually, Z was correlated to X2 to the R1, Y2 to the R2. In particular, Z is correlated. So we have the probability distribution Py and P of Zx. Okay. So the full probability distribution will be Px times Py times Z, which is correlated to Xy. Okay. But here, Z is only correlated to X. So just this part to be more clear, it is Px, okay, P of Z given X. It's no longer Z given X1, but Z. Is this clear? I mean, that's all you have to see. So then, of course, this is less than probability. So I'll now write Py, Px, P of Z given X. Okay. So this will be, this is the case for, okay, so here I'll now play it against F2. So F was the point was minimum, so it's less than F2. And remember, F2 was the hypothesis test between the full joint distribution, and the negative hypothesis was precisely what we have out. So yeah, and of course the number of such guys, I'll write it somewhere. So how many guys are there? So this is 2 to the R2 minus 1 such candidates. So this is less than, so 2 to the R2 minus 1 candidates, and the probability that it fools F2 will be 2 to the minus I epsilon min Y to Zx. So the negative hypothesis will be like the product distributions on Y and Zx. Y and the product distribution Zx. Even clearer, Y and the product distribution. Product distribution Y and the distribution Zx, the joint distribution Zx. So that's, and a similar analysis you will have when m is not equal to 2 to the R1, but n is equal to 2 to the R2. So what are the, so now I want all these errors to add up to less than epsilon or something like that. So what do I need? For this contribution to be small, so I need that R1 plus R2 is less than I epsilon min y colon z. Okay. Then for this contribution to be small, I need R2 to be less than I epsilon min y to zx. And similarly, now you can believe me when I say that we have this third one. In the third case, R1 is less than I epsilon min x to z. Yeah. So is it now clear to everybody? The three constraints come out naturally in this analysis. Yeah, Hari, clear? No?
Yeah.
Yeah, good. So that's it. We have got the rate regions, and yeah, I mean, you put in those log 1 by epsilon terms and all that. So like the three contributions to type 2 error will all be less than epsilon each. So the overall type 2 error maybe is less than 3 epsilon, and then type 1 error is less than 3 epsilon. So everything put together some 6 epsilon error. Okay. You can change those constants. So that's it. So ignoring that log 1 by epsilon thing, we have got our achievable inner bound. So we'll stop, but I want to make a final remark, which will become very crucial when we look at the quantum analog of this. Like all parts of this theory, the point-to-point noisy channel theory, then even the MAC will go through in the quantum. Okay. But there's one part which will become non-trivial. Okay. So that part is,
sorry.
So it's not funny, it is not trivial. So that part is really, I mean, what we did out here. Yeah. So to define Charlie's decoding strategy, we had defined hypothesis test F, which was the intersection of the hypothesis test, the pointwise result. Okay. So as I kept saying, this is like an intersection. Now, classically, the intersection is very easy to do. I mean, often papers don't give a second thought. Okay, so I mean, if you are thinking of your hypothesis test as subsets, then it was actually the intersection of subsets. If you have a slightly more sophisticated view of hypothesis test like this, then it is the intersection of the corresponding fuzzy sets, or rather the minimum. Okay, and then often, like in multi-terminal channel theory, there will be like intersection arguments, or there will be union arguments. So you can also define analogously. Okay. So if required for some other application, I can define analogously this quantity. Let us say G, I can define it to be F1 union F2 union F2. Okay. So if you are thinking of hypothesis test subsets, then it's the union of the subsets. And if you are in the fuzzy world, it's the union of the fuzzy sets. In other words, it is the pointwise maximum. Okay, so G XYZ is the maximum of these quantities. Okay, and minimum and maximum behave very well classically, and things go through. You don't really have to give a second thought. I mean, so unions and intersections are like very natural. But we will see when you do the quantum analog that we have no good notion of intersection, no good notion of union. It is deeply related to the fact that quantum probability is inherently different from classical probability. Classical probability is really, I mean, intersection of sets. I mean, even if you call it fuzzy sets, it's still intersection of sets and something. Quantum probability, the sets get replaced by subspaces of a vector space. And if you try to intersect subspaces, you typically get the trivial zero subspace. Okay. So even though, like, let us say all the three subspaces are pretty big, the intersection can become trivial. Whereas if you have three sets which are quite big, the intersection cannot become trivial. And intersection should continue to remain non-trivial. But this is where things are different. Another way to see it is that the in classical probability theory, like we are dealing with like numbers, okay, and I mean real numbers, and real numbers commute under multiplication. In quantum probability, the real numbers will get replaced by Hermitian matrices, okay, and the Hermitian matrices do not commute under multiplication in general. And when these problems are related, and amazing things, I mean, start happening, and some very obvious things start happening. So it is a non-trivial challenge to make this argument work for quantum. But we'll get to that. I will not get ahead of myself. But I just
have one comment here. So
yeah.
I mean, even in quantum, there are ways you can do intersection in asymptotic IID that are not as involved as the one-shot part. But the one-shot is really outstanding, as in, yeah, it's
I mean, the one-shot makes these issues of minimum and maximum very clear. No, but even in the IID quantum analog of this problem, we don't have any good way of doing intersections and unions. So, I mean, it's not as if the problem is with quantum one-shot, but not with quantum IID. So the same problem exists even in quantum IID, at least for the Mac problem, Mac time.
Anyway. I'm just saying that in IID, there is a little more structure, as in you can sort of, I mean, I don't want to get ahead of myself, obviously, but I mean, you can use the Jordan's lemma and say that angles are small and do all sorts of things, which you cannot do. That is precisely what you cannot do. You have no control over the angles in one shot. That's where things really hit.
Yes, in some cases, but I mean, even Jordan and all that do not help for the Mac problem, the IID quantum Mac problem. So, yeah. So, I mean, you are probably thinking of other applications. And we don't have to bother about those applications in the course, but yeah, the point that I want to say, I mean, that point, this problem or this bottleneck does not go away in quantum IID. Okay. So this bottleneck is a quantum bottleneck. It's not really a IID versus one-shot bottleneck. Anyway, so what I want to emphasize is that I mean, if you read proofs in Elgamal-Kim, they'll be doing unions and intersections and not even tell you. So we will see another example where they have done it, classical thing, and they haven't told you that. Okay, so sort of the one-shot theory forces you to think of these things. Okay, and yeah, and we'll see. I mean, we'll next see the broadcast channel and where there is a union going on. I mean, again, you can go and read the Martin's inner bound with common message from, sorry, Martin's inner bound without common message, simple Martin's inner bound for the broadcast channel. And nowhere will you feel that there is a union intersection issue, but there's a union issue. Okay. So we will see it next. Proof will be very simple, but in the one shot, we'll really chase the union issue and and address it head on. So the one shot sort of forces you to think of these issues which are brushed under the carpet. I mean, you cannot always overcome them, but yeah, it kind of makes you think clearly about aspects of a problem. Anyway, so I'll stop now. Any questions about this material? Okay, so I'll see you on Tuesday. Next.
Pranav, can you upload?
Yeah. But I'll upload this by end of the day. Yeah. I thought I will fix. I mean, whatever. I'll re-record some parts of the lectures which I didn't like. Okay. So I thought I'll just record it myself and then put it up for better thing. But I think that's going nowhere. So it's better to put up the material which is already there. You're right.
I mean, even if they're not polished, like you can put up as private videos and post the link in the Slack.
Correct. Yeah. The earlier videos were actually public videos. So, but no, I'm not afraid of making fool of myself in front of the public world. Anyway, I think nobody else is going to look at this. So yeah, I'll put up the video. At least, I mean, you'll be able to access the videos. Yeah, the same YouTube. Okay.
Pranab,
Mm-hmm.
you
Stop the
meeting
record.
sometime tomorrow or today?
Tomorrow, not
Tomorrow? Okay.